So in the remaining time, I would like to talk a bit about the proof of our theorem. And in order to prove the theorem, we use a so-called Lyapunov-Schmidt reduction. And this approach is based on previous work of Brent and Eichmann, and also of Eichmann and Chodos, where they study large stable constant mean curvature spheres and asymptotically Schwarzschild manifolds. Okay, and to motivate what's going to follow a bit, we're going to suppose that uniqueness in our result fails. So if uniqueness fails, we get a sequence of area-constrained Wilmer spheres that do not belong to the asymptotic family and that avoid a larger and larger compact set, so where inner radius diverges, where the ratio of area radius versus inner radius remains bounded, and where the trace of second fundamental form converges to zero. And under this assumption, you can show that if you rescale these spheres by the area radius, they in fact converge to a round sphere. So you really get very precise analytic control over these spheres. Okay, and for this reason it might seem like a good idea that you study area-constrained Wilmer surfaces that arise as perturbations of coordinate spheres. Okay, so why do we need these assumptions? So the first assumption seems reasonable because the further you go to infinity, the more Euclidean the metric becomes, so it seems likely that you can actually say something reasonable about the geometry of these surfaces. Then the third assumption over here ensures that the surface becomes closer and closer to a round sphere in W22, so this also might seem helpful. But why do we need this assumption in the middle over here? And the reason is the following. So the curvature estimates for area-constrained Wilmer spheres tell you that you can bound the second fundamental form from above by a constant times the inverse of the area radius, plus another constant times the mass times the inverse of mod x. Now it turns out that the second term over here cannot be removed because this owes to the contribution of the Schwarzschild metric, and this actually causes a lot of trouble. Because if you now rescale these spheres sigma I by the inverse of the area radius, then the second fundamental form scales by lambda. So the first term over here is still fine, but then the second term looks like something like lambda over mod x. And now if lambda is a lot larger than rho, then this term actually can become very large, so that you completely lose analytic control over these spheres over here. And if this happens, then it becomes very difficult to say anything meaningful about these surfaces. And for this reason, this scenario where area radius is a lot larger than inner radius is by far the most difficult to study. In any case, moving on with the proof, we're going to assume that the total mass is equal to 2, so this is just a renormalization. And then we're going to consider the coordinate spheres Si lambda. They have radius lambda and barycenter lambda times psi, where the modulus of psi is uniformly bounded away from 1, so it's either less than 1 minus delta or larger than 1 plus delta. And this just ensures that area radius and inner radius are comparable for these spheres. Okay, and then we have the following lemma that for area lambda sufficiently large, you can perturb the sphere Si lambda by a function U psi lambda, such that the graph of this function, which we're going to call sigma psi lambda, first of all has area radius equal to lambda, and second satisfies the constrained Wilmer equation up to the sum of first spherical harmonics. Okay, so how do you prove this? This is actually quite simple, because all you need to realize is that under this assumption that mod psi is uniformly bounded away from 1, the difference of the Euclidean metric and the metric G becomes very small, close to the surface Si lambda. Now in a Euclidean space, all round spheres are Wilmer surfaces, and for this reason you can now simply appeal to the implicit function theorem to prove this lemma. Okay, so why can we not exactly solve the area-constrained Wilmer equation? Well, in the Euclidean space, the Wilmer energy is invariant under translations, and this causes the linearization of the Wilmer operator of a sphere to have a kernel which corresponds to translations, or in the language of variations to first spherical harmonics. And for this reason, we can only use this method to solve the constrained Wilmer equation up to the sum of first spherical harmonics. And in fact, it turns out that these first spherical harmonics somehow measure the translation sensitivity of the Wilmer energy of these surfaces over here. Okay, now of course we're interested in when these surfaces are exactly area-constrained Wilmer surfaces and not only up to first spherical harmonics. And for this reason, we define a function G lambda that measures the translation sensitivity of these surfaces. So this function G lambda maps from this parameter space of all psi that are uniformly bounded away from 1, and it maps it to R. And if the surface is on center, so if mod psi is less than 1 minus delta, psi is being mapped to lambda squared times the integral of the mean curvature squared, minus 16 pi minus 16 4 pi times lambda to the minus 1. Now if the surface is outlying, then psi is being mapped to lambda squared times the integral of the mean curvature squared minus 16 pi. Okay, so the reason why we consider this function over here is because the translation sensitivity happens at a scale of lambda to the minus 2. And then we subtract all higher order terms, and it turns out that if the surface is on center, an additional higher order term owing to the mass arises. Okay, and now with what I've said previously in mind, it's not very surprising that we obtain the following lemma, that sigma psi lambda is an area-constrained Wilmer surface if and only if psi is a critical point of this function g lambda. Okay, so what have we accomplished so far? So we started with an infinite dimensional variational problem of finding area-preserving critical points of the Wilmer energy, and now we've reduced this to a three-dimensional variational problem of finding critical points of this function g lambda. Now how can we accomplish that? Well, it turns out that you can quite explicitly compute this function. So more precisely we have the following. We can decompose g lambda as the sum of a function g1, which is independent of psi, plus a function g2 lambda, which depends on lambda, which is independent of lambda, and plus an error term, which decays to 0 as lambda tends to infinity. Okay, now this function g1 owes to the Schwarzschild contribution. It's defined on all of R3 except the unit sphere, which corresponds to a regime where area radius and inner radius are not comparable. And this function is strictly convex on the unit ball. It's strictly increasing in radial directions. And if you approach mod psi equals 1 from below, then this function tends to infinity. If you approach it from above, it tends to minus infinity. Okay, on the other hand, this function g2 lambda owes to the perturbation sigma, because as you recall, the scalar curvature of the Schwarzschild space vanishes. And in fact, you can show that this function g2 lambda is equal to, if the surface is on center, 2 times lambda times the integral of the scalar curvature over the non-compact domain bounded by the sphere Si lambda. Whereas if the surface is outlying, it's equal to minus 2 times lambda times the integral of the scalar curvature over the compact domain bounded by Si lambda. Okay, so what I want you to take away here is that this function becomes smaller if the surface encloses more scalar curvature. And now, as you recall, the scalar curvature provides a lower bound for the energy density. And what this means over here is if the surface encloses more energy density, the Wilmer energy becomes more negative, so the Hawking mass becomes more positive. So physically, this seems to make sense. Okay, so here's an illustration of this function g1. So as you can see, the only critical point is at the origin, which already gives us hope that we can show existence and uniqueness of large area constrained Wilmer spheres. What I want you to notice is that if you get very close to infinity, then the slope of this function becomes very small. Okay, so how do we prove this lemma? So we're going to assume that mod psi is less than 1 minus delta, so that the surface is on center. And then we argue in 3 steps. So first, we suppose that mg is exact Schwarzschild, and we compute the Wilmer energy over sphere Si lambda. So this is a bit tedious, but just a direct computation. Then in the next step, we take the contribution of the perturbation sigma into account. So we check how the Wilmer energy changes if we change the ambient metric. And then in the third step, we take the perturbation u psi lambda into account. So we check how the Wilmer energy changes if we change the shape of the surface Si lambda. Okay, now it turns out that the third step is very technical and very involved, and actually makes quite the bulk of our paper, so I'm not really going to talk about that much. But the second step is, I think, more geometric, so I want to give you a quick outline of that. And for the second step, we consider the so-called Einstein Tensor, which is the difference of the Ricci curvature and 1/2 times the scalar curvature times the metric tensor. And then if we integrate the Gauss equation and use the Gauss-Bonnet theorem, then we find that the integral of the mean curvature squared is equal to 16 pi, plus 2 times the integral of the length of the tracer's second fundamental form, plus 4 times the integral of the Einstein tensor of the outward normal u. Okay. Now in a flat Euclidean space, this integral over here vanishes, and this property is conformally invariant, so it also vanishes in the Schwarzschild space. And we can show that even with respect to this perturbation sigma, this integral over here is smaller than the scale we care about. Okay, now on the other hand, to compute this integral over here, you make 2 observations. So the first one is that in the Euclidean space you can extend the unit normal of a round sphere in a canonical way to all of R3, namely by defining a vector field Z to be lambda to the minus 1 times x minus lambda psi. And then even with respect to the metric G, this is then still almost equal to the outward normal. The second observation is that the divergence of this Einstein tensor actually vanishes. And for this reason, in order to compute this integral, you can replace 1u by z, then appeal to the divergence theorem, and then show that this is equal to the integral over the non-compact domain bounded by S I lambda of 1 over 6 times the scalar curvature times the divergence of z, minus 1 over 2 times the inner product of the Einstein tensor and the conformal Killing derivative of z plus an error term. Okay, now the divergence of z is essentially equal to 3 times lambda to the minus 1, so this integral over here gives you the contribution of the perturbation sigma. On the other hand, this vector field z is a conformal Killing vector field, so in the Euclidean space dz vanishes. And for this reason, dz is one order smaller than the divergence of c, and for that reason you only see the Schwarzschild contribution in the second integral over here. Okay, so now that we've proven this lemma, how can we put that to use? And this happens in the following proposition. So now we suppose that the scalar curvature satisfies the growth condition, namely that mod x squared times the scalar curvature is radially non-increasing. And what you can then show is that the function g2 lambda is convex on the unit ball and radially increasing outside the unit ball. And in particular, what this means is that the function g lambda has at most one critical point if lambda is sufficiently large. Because we know that the function g1 is strictly convex on the unit ball, so something strictly convex plus something convex plus error is still going to be strictly convex. And outside the unit ball, the function g1 is strictly radially increasing, so something strictly radially increasing plus something radially increasing plus error is still going to be strictly radially increasing. So here I've cheated a little bit because, as you recall before, the slope of the function g1 becomes very small as psi approaches infinity. And for this reason you need very precise error control to actually make this conclusion over here. But again, this is very technical, so I don't really want to talk about this. Okay, so now I also want to give you a quick outline of the proof of this proposition. So we're only going to show that the function g2 lambda is convex on the unit ball. So we'll consider two vectors psi1 and psi2 whose modulus is bounded from above by 1 minus delta. And what we're going to show is that the gradient of this function g2 lambda is monotone. So we're going to consider the difference of the gradient at psi2 minus the gradient of the function g2 lambda at psi1 times psi2 minus psi1. And you can easily compute that this is equal to 2 times lambda times the integral over the sphere as psi1 lambda of the scalar curvature times the inner product of psi2 minus psi1 and u minus the same integral over the sphere as psi2 lambda. Okay, so now the scalar curvature is non-negative, which means that these integrals have positive and negative contributions. And the positive contributions happen on the hemisphere where psi2 minus psi1 times nu is non-negative. So we're going to call S1 plus the hemisphere where psi2 minus psi1 times nu is non-negative. We're going to call S1 minus the hemisphere where this inner product is non-positive, and likewise for psi2. Okay, now if we use that the scalar curvature is non-negative and if we also use the growth condition, we can show that the positive contribution in this first integral, so the integral over the hemisphere S1 plus, is larger than the positive contribution of this integral over here, which with the minus sign becomes a negative contribution. Likewise, we can show that the negative contribution of the second integral, which with the minus sign becomes a positive contribution, is larger than the negative contribution of this first integral over here. And putting these inequalities together, what we obtain is that this term over here is greater or equal than 0, so the gradient of g2 lambda is monotone, and this proves the proposition. Okay, so to give you a little more detail, let's focus on this first inequality over here. And the hemisphere S2 plus is the solid black line over here, and the hemisphere S1 plus is the solid black line over here plus this dotted line. Okay, now in order to compute these two integrals, what we first do is that we throw the integral over the dotted line over here away, using that the scalar curvature is non-negative. And then what you can notice is that you can connect every point on S2 plus to a point on a solid black subset of S1 plus by shooting a radial line through the origin. And now you can compare the scalar curvature along this radial line using the growth condition. And using that growth condition, you'll see that the integral over this solid black line over here, which corresponds to the subset of the hemisphere S1 plus, is actually larger or equal than the corresponding integral over the hemisphere S2 plus. Okay, so this completes the proof of the proposition, so let's now finally talk about the proof of the main theorem. So if the scalar curvature is non-negative, then the function g2 lambda is also non-negative. So this means that the function g lambda is larger or equal than the function g1 plus some error term. Now we know that the function g1 blows up as mod psi approaches 1. So this approaches infinity as mod psi approaches 1. So in particular, there has to be a local minimum psi lambda somewhere in between. And as we have argued before, this critical point psi lambda corresponds to an area constrained Wilmore sphere. So this is how we prove the existence of an asymptotic family by area constrained Wilmore spheres. Now regarding uniqueness, we're additionally going to assume that the growth condition holds. And if uniqueness fails, then as before, we can find a sequence of area constrained Wilmore spheres sigma I that avoid a larger and larger compact set, so where inner radius diverges, where area radius versus inner radius remains comparable, and where the trace of second fundamental form vanishes. But none of these spheres belong to the family constructed in the first step. Okay, so as before, we rescale these spheres by the inverse of the area radius, and then using curvature estimates, we see that they become closer and closer to a round sphere. Now, if we use the local uniqueness statement of the implicit function theorem, we'll see that these spheres actually arise in our Lyapunov-Schmidt reduction in the sense that they're equal to sigma psi I lambda I for suitable psi I and lambda I. But now, we know that these spheres sigma I are area constrained Wilmore spheres. In particular, psi I has to be a critical point of the function lambda I. But we also know that the function g lambda I only has one critical point, so psi I has to be equal to psi of lambda I. But this in return means that this surface sigma I actually arises in this asymptotic family that we constructed in the first step, so we obtain a contradiction and the theorem is proved. Okay, so I'm at the end of my talk today. Thank you very much for your attention.